Matter is anything that occupies space. There are three states that matter can be in: solid, liquid, or gas. Let's take a look at the distinguishing physical properties. In terms of their shape, solids have a fixed shape, liquids do not have a fixed shape but takes up the shape of their container, and gases do not have a fixed shape. In terms of their volume, solids and liquid have a fixed volume but gases do not have a fixed volume. In terms of their compressibility, solids and liquids cannot be compressed or gases can be compressed. These are the particle diagrams of solid, liquids, and gases. Solid particles are packed closely in neat rows and columns. This is called a lattice structure. Liquid particles are more spread out than solids, however, there still exist some particles touching others. Gas particles are all spread out with none of them touching each other. Kinetic particle theory is a model that simplifies the behavior of solid, liquids, and gas particles. It consists of three characteristics: particle separation, arrangement, and motion. Let's describe the properties of solid, liquids, and gases in terms of the kinetic particle theory. In terms of particle separation, solid particles are touching, some liquid particles are touching, and gas particles are not touching. In terms of particle arrangement, solids are arranged in a regular pattern, liquids are arranged irregularly, and gases have a random arrangement. In terms of particle motion, solids can only vibrate in place, liquids have a slow random motion, and gases have a quick random motion. The three states of matter, solid, liquids, and gases can become one another. The different processes that happen are: solid to liquid is melting, liquid to gas is boiling or evaporation, gas to liquid is condensation, and liquid to solid is freezing. We can also interpret changes of state in heating and cooling curve. A heating curve shows the temperature of a substance upon heating it up. Slanted line shows an increase in temperatures when heating. This means that the substance is a certain state. Horizontal line shows a constant temperature, although heat is still added to the system. This shows that a change of state is happening. In the first section, the substance starts out as a solid. As we heat the solid, the temperature increases correspondingly. At a certain temperature known as the melting point, the solid particles have enough energy to overcome their forces of attraction, so they break their bonds and turn from solid to liquid. The particles are more free to move about. This is melting. Further heating the liquid gives us an increase in temperature. At segment DE, a certain temperature known as the boiling point, the liquid particles have enough energy to overcome their forces of attraction, so they break their bonds and turn from liquid to gas. The particles no longer touch each other and move around much more freely. This process is boiling. The curve ends here as we have reached the final state from heating. Continuing to heat the system will not incur any new change of state. This is a cooling curve. It is exactly the opposite of the previous heating curve. Once again, all slanted line shows a steady decrease in temperature when the substance is cooled. The substance is therefore in a certain state. Horizontal line shows that a change of state is happening. In segment AB, we start from a high temperature gas and begin cooling it down. As we cool the gas, the temperature decreases. At a certain temperature known as the condensation point, the gas particles do not have enough energy to continue being a gas, so are forced to come closer together and turn into a liquid. This is condensation. The liquid is cooled further and the temperature decreases. At segment DE, a certain temperature is reached, called the freezing point. This is when liquid particles do not have enough energy to maintain being liquid, so are forced to come closer together and become a solid. This is freezing. If the solid continues to cool, no further changes of state occur. Given melting and boiling points, we can also deduce the state of a substance at a specific temperature. For example, substance X has a melting point of 0 degrees Celsius and boiling point of 100 degrees Celsius. What is the state at 12 degrees Celsius? To solve this, first draw a line linking the melting and boiling point. The melting point always comes first, followed by the boiling point. Continue by writing the states of matter in each segment. First will be solids, then liquids, then gases. Finally, find the desired temperature, which is 2 degrees Celsius, and plot it on the line. In this case, substance X is a liquid at 2 degrees Celsius. Effect of temperature on gas. As temperature increases, gas particles have more kinetic energy, so they move faster. This is shown by the animation below. If the gas particles are in an expandable container such as a balloon, the container starts expanding as volume increases. If the gas particles are in a non-expandable container, pressure builds up. Effect of pressure on gas. When pressure increases, the volume of the container must have decreased. Conversely, if the volume of a container increases, pressure decreases. They show an inverse relationship. Note that the kinetic energy of particles remains the same, so they move at the same speed. If the volume is smaller, gas particles collide with the walls more frequently, hence build greater pressure. Diffusion is the random movement of particles from a region of higher concentration to a region of lower concentration. This is a simulation of diffusion. Think of diffusion as the mixing of particles. Particles start from a region of higher concentration, which is at the bottom right, shown by the red particles. As particles randomly collide and move, the red particles soon end up in a region of lower concentration, which is the left side. Over time, the grey and red particles would have mixed evenly throughout the box. A factor that can affect the rate of diffusion is relative molecular mass. Because the mass of molecules is very small, we use a relative mass, but the mass of molecules is compared to 1/12 of an atom of carbon-12. So relative to each other, the masses of molecules are obtained. Calculating relative molecular mass. Let's calculate the relative molecular mass of hydrogen chloride as an example. Hydrogen chloride contains hydrogen atoms and chlorine atoms. These are the elements of hydrogen and chlorine from the periodic table. There are two numbers. The mass number is always the greater number. After finding the masses of both hydrogen and chlorine, add them together to find the relative molecular mass of hydrogen chloride. 1 plus 35.5 equals 36.5. Experiment to investigate the effect of molecular mass. This experiment is to show how the rate of diffusion changes based on different molecular masses. On the left of the tube is ammonia soaked in cotton wool, and on the right is hydrochloric acid soaked in cotton wool. When these substances are soaked into cotton wool, they eventually give off their respective gases, ammonia and HCl gas. When these two gases react, they form a white cloud of ammonium chloride. To see where the white cloud forms, calculate the relative molecular mass of ammonia and hydrochloric acid. For ammonia, the nitrogen has a mass of 14 and each hydrogen atom has a mass of 1. There's 1 nitrogen and 3 hydrogen atoms, so the total mass is 14 plus 3 times 1, 17. The relative molecular mass of hydrochloric acid is 36.5. The greater the relative molecular mass, the slower the rate of diffusion as the substance is heavier. So because ammonia is lighter, it diffuses faster, and so the white cloud forms closer to the right hand side. That concludes this chapter on states of matter.